talking first. He's a 4th year math and computer science student. And he's a research assistant and security engineer and just a bunch of stuff. But I think he's got a really interesting talk for us today. Let's hear him.
Can you make it so that it's also the slides? There we go. There we go. So now we can actually see the slides. So my talk today, if you haven't seen the promo, is pretty much, well, it's titled Writing Code Without Writing Code. But it's a bit of a lie because we're going to write a bit of code. We're also going to look at a lot of code. So actually, we're going to do a lot more work for a lot less. But it looks cool, and that's what matters. So I want to start off with this, and you can't see that at all. So let me turn the lights off.
Yeah.
Is that the ones?
Forward, I think it's labeled forward, I think.
Oh, Bohr, that's all your lights.
Oh.
Everybody see that, right?
It's okay, it's good.
Sweet. Better.
Is that code?
It is some code, and there's 2 bits of code which do something kind of similar. And if you can see, there's 2 functions there, and pretty much I like getting audience engagement, so I want to see a raise of hands for option A or B. Well, actually, no. What do you think this function does? Also, anyone that's taken 3100 is not allowed to talk.
Can you zoom in a little bit?
Oh, yeah. Can.
Does it return X?
X? It does return X. In the interest of not staring at the same lines of code for too long, I'll just reveal what one of them does on the next slide, which is called masked function because I copied it incorrectly. One of these describes the Fibonacci numbers squared. And then you calculate the nth Fibonacci number, and that is your input to the function, and it returns to you that the Fibonacci number of that Fibonacci number squared. So you give it 3, calculates the 3rd Fibonacci number, and returns that number there squared. So looking at that code right there, it's not quite very intuitive that that's what it does. But it has some nice properties, and the bonus of this like snippet of code here is that we didn't have to think, well, I mean, we did have to think about it, and we'll get to that in a bit, but we didn't have to stare at that and go. Additionally, it has some extra properties in that how you might solve that normally is by generating each Fibonacci number first and then squaring it, right? That has some efficiency problems. This here is quite efficient code in that it's O of n as well. So, first, I'm actually going to start with a bit of history. And you'll notice the slides are a bit munted. That's because I had to change laptops at the last second. And it doesn't work on multiple things because software. As with a lot of computer science, a lot of this theory was developed a fair while ago and has only come to fruition recently. So we start off with these 2 guys right here, Tony Hoare and Ebsco Dijkstra. Now you might know Dykstra. You probably don't know the name Tony Hoare. Tony Hoare was a massive proponent in the field of formal arithmetic, which is what all this surrounds, and we'll talk about him in a second. But he pretty much came up with the underlying theory for all of this, which wasn't touched for another 50, 60, 70 years until the last 20 years, really, when we realized that, hey, no, this stuff is actually pretty useful. Now, Dykstra, actually, I'm not going to talk too much about them now, because I'll talk about them in a second. But there's a couple other notable mentions down there as well. Names like Bertrand Russell, Kurt Gödel, and Alan Turing are all names you've probably heard before in relation to computer science, but probably not specifically on what they do. And Bertrand Russell, he had this idea of he pretty much helped formalize sets in the early 20th century, and he helped form the basis for what was formal reasoning about sets and just in general. Kurt Gödel came along and helped formalize that a bit further, but also brought about Gödel's incompleteness theory, which screwed up a bunch of stuff and pretty much said that we can't know everything. Anyone who's done a bit of set theory probably will be familiar with that. We don't worry too much with Gödel here, except for the fact that Gödel tells us that we can't know everything about our programs sometimes, which is a bit frustrating when we want to reason about programs and we want to know everything about them. And then Alan Turing, of course, is a name everyone is familiar with. So Tony Hoare, what did he do? He came up with this idea of so Hoare gave us Hoare logic and Hoare triples. Now, what are those? Hoare triples is a set of 3 things, as you can see up there, P, C, and Q. And this is pretty much a way that we can describe a command. Now, what is a command? A command is literally anything that we run. So it's your program, it's your function, it's your line in a function, it's the opcode. It's anything that gets executed is something that you can reason about. So, and you can reason about doing something. I have a ball and I throw it. That is a program, right? I throw a ball. What are the requirements for that? The requirement is I have to have a ball, and the outcome, I suppose, the post condition is that the ball is no longer in my hand. That would be a description for something you can do. And so we describe all of the states of our program by looking at the instructions, and we look at our program line by line. We say, take the line of code, we say what needs to go in before it, the precondition, and we say what comes out of that, the post condition. So Tony Hoare formalized this idea and gave us a bunch of rules about reasoning with these triples, which we can use to reason about programs on the whole. Now, this on its own is pretty strong, but it's not enough to reason about entire programs, especially when you start getting into non-trivial cases where your program is not just one line of code. And that, well, actually, no, sorry, I'll come to that in a second. I'm getting ahead of myself. I want to talk about this quickly first. So this is a very fairly simple sample, the swap function. So if you have two elements and you want to swap them, the way to do that with just three variables is you just set a temporary variable, set that to one of them, then actually swap them and set the other variable to that. So this here, so we can reason through this function on its own, right? So taking a look at this, and I don't have the next slides, but we come to the end, and no, that is getting ahead of stuff. Okay, no, before we actually go through and reason about this, the problem is that we need to find out what P and Q are, right? So currently we know that we have some state beforehand and we have some state after. We know that we want to have two elements, A and B. They can be whatever we want, integers, objects, whatever. And we want to swap them so that A refers to B and B refers to A. And that's our post condition, right? So we have what we want to start with, and we have the outcome, the pre and the post conditions, but we don't know how to get from A to B, or from P to Q in this case. So that's where Dijkstra comes in. So Dijkstra is a name pretty well known in the computer science field, but probably only because you know Dijkstra's algorithm. So Dijkstra came up with this algorithm which lets you find the shortest path, shortest optimal path between 2 points in a network. But that's not the only thing he did. He did a fair bit of other things. Dijkstra is a large part of the reason we have concurrency and threading in our programs. So he spent a good chunk of the 70s and 80s coming up with models for how computers can handle information concurrently, how we can have two processes on a CPU running, and how we can have our memory not stuff up because of that. Another interesting note actually on Tony Hoare is he came up with the idea for the null pointer, which he many years later described as his worst mistake, because you can get through programs and reason about things without having, not reasoning in this sense, but you can write programs without null pointers. And his invention of it, he said, was really just a get around because he was too lazy to come up with do the actual work. So we just introduced it to a programming language and it stuck, and now we have a heap of bugs. So blame Tony for that. But anyway, so with Dijkstra came around and took Tony Hoare's triples and said that we can reason about our programs by effectively concatenating these. How do we concatenate them? By implications. So if we have a chain of commands, with each with a pre and a post condition, then the post condition of one is effectively then becomes the precondition for the next, or rather it has to imply that. And so with that logic, we can reason through our program downwards in that if we start with P and we have a chain of commands, each has to imply the next until we get to Q, or at least hopefully by the time we get to Q, we have that all of our operations with that input implies the output. And that's largely what reasoning about programs is. It's starting with a statement and proving that with a command or a sequence of commands, you get a certain output, or at least that you're proving whether that happens or not. On top of, and this is called the strongest post condition reasoning, but the reasoning that's most often done when you look at a program is weakest preconditioning. And so that is effectively doing the opposite, but doing the same but in reverse. So you start with your post condition, what you want, and you reason backwards to prove that that gives you the original, what you would put into that function. And there's an extra note down here that this introduces a little like anomaly in the sense that when you have an implication with A implies B, logically how that's defined is not A or B, and which gives us the statement that false technically implies anything, and anything implies true. So this comes back to, not bite us, but we use this a little bit later. We'll come to that. But Dijkstra lets us reason about this now. So we have our function, swap. This is what we want at the end. We want A to be pointing to B, and we want B to be pointing to A. And so then we make a substitution for B, because that's what our program does for temp. So star B becomes temp, then star A becomes B, and then finally temp becomes A again, and we get that star B is equal to old B, and star A is equal to old A. And so we've shown, we can show, like as is shown here, that if we have this program, we start off with something that points, two things which point to an element. If we execute this program, we will have that they are swapped around. Now, the important thing to note here is that this here is not exactly the requires clause. We have that the order of these is swapped around, and the reason we can't just say that this is the precondition is that we say that this implies the precondition, our requires clause. So once we have that this implies the requires clause, we can say that this program here, the swap function, is correct. So, things that we care about when reasoning about programs are some things which get a little bit more complicated, like reasoning about loops. And that comes into a question of, does our program halt? That's where Gödel comes in again. Similar thing, calling functions. How do we reason about calling a function? Is it just we take the host and preconditions and chuck them in? The answer is not quite, but we won't worry about that here. And again, we have to have the question of, does it halt? Because we have recursive cases. And again, Gödel comes in. Then we have other things which prop up in programs, like pointers and arrays and objects, things which aren't very intuitive to reason about, all of which have methods to reason about when defined and have been explored, but we won't worry about them here. Things we will worry about, if statements we won't actually go into, they're just cool things to know. Substitution, so we did that a little bit just in the swap function then. But effectively, you have your statement, and when you make a substitution, like x equals 3 plus x, you just substitute that into your reasoning, and then you can say this. So how that works, the example there, is if you start off, when you read these, you should be reading from the bottom upwards, because that's our weakest preconditioning reasoning. So unintuitively read from the bottom. So we start off, our result is that x is greater than or equal to 0, and if we apply the operation x is 3 plus x, then that means before that, we must have had that 3 plus x is greater than 0, which tells us that x is greater than or equal to 3 originally. So that means that if we start with x greater than or equal to 3, and we apply the operation x equals 3 plus x, we know that x is greater than or equal to 0. And again, right down at the bottom there, we get into loops. Now, loops are a lot more difficult or more interesting to reason about, because we get into the idea of invariants. So, and I realize this is also throwing a lot at you, but invariants are their own ballpark, and it's an ongoing field of research because we don't know how to reason about them properly. Or not completely, at least. So what is an invariant? An invariant is just something which doesn't change. So invariant, just something stays the same. With regards to our while loops, or just any sort of loop in a program, we have something which doesn't change in our program, and which we can use to reason about it. Now we know that on entry to this loop, this invariant will be true, and at the end of this loop, it must also be true, which tells us that when we come out of the loop, this must also be true. So the reasoning we can have about this is that if we generate a bunch of invariants, which is a statement about our loop on variables in our function which don't change, then we know that these must hold after the loop, and we know that this g here must not be true because we come out of our loop. This g is called the guard. This is just what you put inside your if or your for statement to have it end. So, as I said, this is ongoing research. We do research here at UQ with that. There's a team in ITEE who are currently working on this, and there's some teams down at ANU and scattered around Australia. But yeah, that's a field we contribute to, which is pretty cool in my opinion. So they're hard to reason about, but they're not impossible. And we do have a couple techniques for these. Some of which are listed here, not all of which we need to go into, but some of which we will use in a second. So we have invariant negation of guard. You just take things in your postcondition. You take things in your postcondition and chuck them into your invariant, but you swap them around and use one for the guard. I probably won't go through and explain each of these individually because they need examples alongside them. But know that we just have ways that we can reason about loops, and we can generate these invariants and say things about our loops and our programs that don't change. On top of this, we can, and as a side note, when we're reasoning about our programs, we reason upwards, right, as I said, which means that due to that little quirk that I explained earlier, we can strengthen things as we go upwards. So that means that when you start, like if you read the example here, if we start with x greater than or equal to 0, greater than or equal to 100, then we can say that x greater than or equal to 50 or less than or equal to 50, oh, that shouldn't be 50, that should be something like 70, sorry, that's a typo. And we say x equals 51, each subsequent one is a stronger statement about our variable x, but going down, each implies the other. If we were to start with x is 51, then it is true that x is between 50 and 70, and it's also true that x is between 0 and 100. So that means that going up, we can make stronger statements about the variable that we're concerned with, and that helps us when reasoning about our programs, because we can simplify things a bit, or we can introduce things. So, the scenario that we had with a broken image, because this is not working, is that we have the example from earlier, right? We want to create a function. Our boss gives us a task. He wants the nth Fibonacci number squared. He wants it to be 100% correct. He wants it to be fast, and he wants to only use addition because he's a psychopath. So how do we do that? So immediately, like our normal techniques are kind of annoying because if we try to just calculate Fibonacci numbers, they're not difficult to compute, but they're inefficient to compute, right? And there are other ways we can do it, but we don't want to code, and he wants exactness. He wants to know for certainty that he's going to get what he wants. So we first describe our problem, right? We start with the specification. We know that our input is going to be a number greater than or equal to 0, and we know that we want to return the Fibonacci number squared, so the nth Fibonacci number squared. So we can assume that we have some knowledge about the Fibonacci sequence because that's a sequence that we know. And so we can assume, this is sort of a trick that is used in reasoning, but effectively we say we know what the nth Fibonacci number is, so we know that if we have this nth squared number, we know what it is. It's a little bit roundabout, but effectively we can just make this claim that we know that it returns Fibonacci fib n by fib n. So we can then create this skeleton of a program. We know that we're going to need some sort of while loop, and we know that we're going to have some variables to start off with. So we're going to return this value x at the end, and I is going to be our iterator for the loop. And we can generate some very basic invariants. So things that don't change in our loop, we know that I must be between 0, because it starts off at 0, and n, and we only have incremented. So that never changes. And as soon as I hits n, it leaves, so this stays true the whole time. And we can also make the second invariant that every time we go through our loop, we're going to be at the next Fibonacci number squared, our variable x. So we start off with this, and we introduce this at the end because, as I mentioned earlier, in a loop, an invariant is true at the start and at the end. So inside the loop, we start with the invariant, and we move up, just substituting and applying all our other reasoning, other tools of reasoning that we have, until we get to the start, where we have to have whatever our logical statement is implying all of our invariants again, because invariants have to be true at the start and at the end. So we start with our invariant, and we make the substitution I plus 1. I is I plus 1. And we reason back through this, and we get to this point here. Now, this is where strengthening comes in, because if we have I is between less than or equal to -1 and less than or equal to n minus 1 and greater than or equal to -1, then this statement here, that I is between 0 and n, is a stronger statement, so we can make that claim as we move up. And then we can split this up, because I less than n is the same as saying I is less than or equal to n, and I is not equal to n. And this gives us this part of the original invariant, right? So at this point, we have part of our invariant, but then we get to this tricky part. We want to make x. Currently, we have that x is equal to the next Fibonacci number squared. So that's the result we want at the end, right? But we're kind of stuck because we want that to imply this statement up here, that x is actually the current Fibonacci number squared, which in our current program, we don't have anything to do that, right? There's nothing transforming x into that. So we must have something in the middle. We know that we must have something in the middle, so we can just wish for that. And we wish for something, and we call it y in this case, sorry. So we wish for this variable y, and we set x to be that value. And then we have that y is equal to this, and we also introduce the invariant that y must be this next Fibonacci number squared, right? Because then when we make the substitution, x becomes what we want, and we get that this will then imply up here. But we get, that's jumping ahead of myself here. We get this statement here, right? So we're not quite there. So we need to then reason about our variable y that we introduced, right? Because we don't know anything about y. We've just introduced an invariant for it, and something will happen to it. So at the end of the invariant tells us that at the end of the loop, again, we start with y is equal to the next Fibonacci number squared. We make the substitution again, and we reason back up, and we get to this stage here, where we have making this substitution, we have I plus 2 as our Fibonacci number, right? But using our knowledge about the Fibonacci sequence, we know that the Fibonacci number that is 2 from now is actually just our current Fibonacci number and the next one added together, right? By the definition of the Fibonacci sequence. So we can make that substitution and say fib I plus 2 is just fib I plus 1. And so then we have this equation here saying that this is multiplied by this, and expanding this gives us the current Fibonacci number squared plus 2 times the combination of the two Fibonacci numbers. This is just expanding brackets. And then the square of the next Fibonacci number. Rearranging this, we see that we already have a variable describing the current Fibonacci number squared, x. We have a variable describing the next Fibonacci number squared, y. But then we have this extra term, 2 times the current Fibonacci by the next Fibonacci, which again, we have no idea what this is. So we need something that we can put in here that implies this. So we have y is currently equal to x plus y plus this weird thing. And this, we know, must imply that y is equal to the next Fibonacci number squared. So we wish again. And we keep wishing for things until we get to the point that we have a statement. So y is x plus y plus this something k, which we introduce. So we set that in our program. We introduce the statement that y must be equal to x plus y plus this k variable, which we then reason about next. And going up through the reasoning, we see that this satisfies the implication. So we get to the next stage and we do the exact same process again. And I won't go through it exactly because for the sake of not boring you, but we get to this stage where we have k is itself. So we reason back up and we get k is 2 times the current Fibonacci squared plus the next, times the next, plus 2 times y. And this is where we come into a bit of a problem, which is easily solved in the fact that this is 2 times y, right? But we don't want 2 times y because our boss said we couldn't use multiplication. So that's easy. We just substitute that y plus y, right? So then we make that substitution again. We get k is k plus y plus y. But there's something cool with this is the fact that we don't have any more unknowns. We're at the point where we know everything that we've introduced. And at this point, we have that it implies what k should be at the start. And we have no more unknowns. So we just set k to be k plus y plus y. This is just summarizing what we know. And we're done. So at that point, we know that if we set x to be y, if we set y, an introduced variable, to be x plus y plus k, if we set k to be another introduced variable, k plus y, that all of these will imply the original precondition. And through a bit of a long proof, you get that it implies all of those invariants put together at the start. And this, with these simultaneous assignments, is our program that we then just reasoned about. So, looking back at this, I'm not expecting to actually remember what those were at the start. The option was A. And this is the program we come up with. So this program is fast. This program is correct because we're able to prove that if we start with an nth number, with the number n, that we can generate the nth number squared. So as long as we input a number that is greater than or equal to 0, it will always give us the nth Fibonacci squared provably. And it was generated by us without actually having to think about writing an algorithm. We just started with a postcondition and a precondition, and we used a bit of reasoning. We thought about it a bit, and we came up with what needed to be in the middle. These values up here, how they were calculated, I know I've just sort of chucked them in. How you get those is that you keep reasoning back up, but like we did inside our loop where we went, okay, this value is missing something. It needs to be k plus y, or x plus k plus y. Use the same thing where you go, okay, we have here that we know need n to be greater than or equal to 0, which means that our k must be 0, y must be 1, and effectively just make a series of substitutions. I'm just skipping over that because the working comes out fairly trivially when you put it down pen to paper, and it's not too important here. But now I've got a little demo, because we have that. So, oh no. That was because I tried to make it smaller. So, third Fibonacci number, 4. So 1, 1, 2, is 4. So we can go 9. Somebody know what the 9th Fibonacci number is? Indeed it is. I can't do that in here, but yes. 5.
0.
Sorry? 0. 0 squared is 0. Although Fibonacci number, when you define it, yes, we should probably set n to be greater than or equal to 1 in that case. or unless you start at 0 plus 1, it's probably okay. But yeah, so this here is executing the code that we just wrote up here. I've just concatenated that there, and we get these, and we can do as big as we want. That might take a bit. It just gave us that. If you ever tried to calculate the 1000th Fibonacci number, it normally takes a little longer than that. And we just squared that. So yeah, there's a demo. So why do we care about any of that? I could have written that algorithm in about 5 seconds instead of just 20 minutes. Because it's a more specific example for a very general problem in the question of security about programs, right? So if we have a program, we want it to do something specific. And if we can't guarantee that it does something specific, then how can we trust it? And the answer is generally you can't. Or you throw it through a lot of tests and you convince yourself that you can trust it. But this reasoning about programs gives us a way to say that if we have this program and we can confirm that it's true, that no matter what we put into it within the bounds we define, it will always give us the certain output that we want. And so that lets us verify things, right? It lets us identify bugs, and it gives us ways to reason about programs that we previously didn't have, which gives us the ability to do things like symbolic execution, which is another field in its entirety where you go through and you execute a program without actually executing it. And so it lends itself to this wide-ranging field that is really only just starting to bloom over the last 20 years because we didn't have the computational power to do it before and nobody really wanted to touch it. And so who does this kind of work and where is it used? All of these big names up here. Recently the Cyro team closed down, so they had this operating system called Cell 4, which was a project they were working on building an operating system but verifying it as they went, so that you could have a fully verified operating system to run your code on and build. It was a kernel that you could build operating systems upon. And that, as far as I know, is actually used in some places like NASA and Tesla. So NASA used a verified operating system on them, one of the Mars rovers, because understandably, you don't want your software to break when it's a couple million miles away. And having to update your operating system is a little hard at that point, and sometimes impossible. So having a verified program and having that sort of assurance, knowing that your operating system is pretty good because then you don't lose money and you have a working rover on Mars. Tesla use it in their autonomous cars, so similar sort of principle. You don't want to accidentally run over somebody. And confirming that your car won't do that is pretty good. Google does a lot of vulnerability research in this area. Microsoft built the tool Daphne, which is a tool you can use to reason about programs. And defense also does a lot of work in this space as well. So to tie it off, just some references. I didn't cite these throughout my talk, but I certainly used them. CSSE 3100, the example that I used is pretty much ripped straight from the lecture slides. But it's a great course, and it's run by Dr. Graham Smith from ITEE. He's a great lecturer. If you have the opportunity to take this course, I couldn't recommend it highly enough. And it pretty much tells you how to do a lot of this and gives you the groundwork that you need to do further research and this sort of stuff. On top of that, 2 books. Program Proofs, this is, I think, the assigned textbook for 3100, but it is actually really good and still in its draft phase. But it pretty much builds you up from the ground up and explains all these in a fairly intuitive manner and goes through reasoning about programs in general. And then we have Communicating Sequential Processes by Tony Hoare, the man himself. It's a book about reasoning about programs with concurrent processes, pretty much exactly it describes. This is kind of along the lines of the work that Dijkstra was doing back in the 70s. But here we have Tony Hoare formalizing it and making it just a little bit better. So yeah, that was my long spiel about reasoning about programs. Any questions at all?
That's fine.
So, would there be a way of knowing that it's the fastest algorithm, like fastest method, and it's still being sound?
That is out of bounds of my knowledge.
Okay.
In the sense, I'm pretty sure you can prove that it's like separate to program analysis. You can prove things about the speed of programs, but I'm not sure if that ties in with this field. I think that's a tangential field.
Okay.
But don't quote me on that as well. Look it up. Yes.
So when you were writing those, when you were coming up with those wishes, weren't you technically also still writing code?
Well, I said I lied to you as well. It's a clickbait title.
So it's kind of like a different method of writing code. So
Yeah,
it's generating requirements instead of.
It's a programmatic way of just figuring out what you need to write, which is also good. And another field I forgot to mention is code generation, because then you get into this idea of if I have a specification, I want to start off with this and I want to finish with this. then if you can tell a program how to do that reasoning, then you can get a program to write code for you instead of having to do that for yourself. So in that way, I mean, I'm not going to do it for this talk, obviously, but I'm pretty sure you could probably go through and make something which writes that. We're also running out of time, I think, so I'm going to stop talking now and let Mitch come up and do his talk. Yeah.
Your talk's way more interesting than mine, so.
Oh no. Thank you very much, Tom. Yeah.
Yes, that's it.
So now we're going to have Mitch speaking about integer programming, which is what you learn in operations research, if you've heard of that before. Mitch is a PhD student. He's also tutoring the operations research course.
Guess
Yeah.
that's it.
Your setup's a lot
Okay.
easier.
My setup is PDF file and HDMI cable. Although I don't know what to do now. Oh, there we go.
Yeah.
Thank you.
That's nice.
Awesome. Am I good to go? Cool. Yeah, so as you can see here, the title of my talk is Paving Paradise More Efficiently, Designing Parking Lots with Integer Programming, and I really hope that at least one person understands that reference. But if not, that's all good. It's a really old song. So what are we doing? So a little bit of history. This problem was originally worked on by some Math 4202 students last year, and I know at least one of them is in attendance at the moment, so hopefully I do justice to the project. But we've taken it a little bit further than they went in that project, and that's cool. So I'm going to be working with a particular example of a parking lot just throughout this talk. I think this is in Germany somewhere. I just lifted this screenshot from a paper that I'll cite shortly. And I think if you look, you can count about 28 parking spaces in this section here. But it doesn't take long to convince yourself. You could probably fit a lot more in if you put a little bit of thought in. But we want to do this mathematically. We want to think about what the best possible parking lot could be. So the first thing we're going to do is we're actually going to convert our instance to a grid of 1 by 1 squares. Here, these grey squares just represent obstacles that we can't put any parking lots or driving squares in. The blue squares just represent the squares that have to be driving tiles in this example. That's just the strip down the side here. But the rest of the squares are free game to contain either parking spaces or driving lanes. And a few rules for the problem. All of the parking spaces are of size 2 by 1, and we're only doing perpendicular parking. You could also consider things like angled parking or parallel parking and that, but that would just require a different model, and you could definitely do that kind of thing. And the driving lanes have to be at least 2 squares wide, and this is so that you can allow bidirectional traffic, room to turn around. I don't know if you've ever tried to turn around in a very narrow parking lot. It's not fun. But also, crucially, every parking space actually has to be reachable from the entrance. And these are the kinds of constraints that you don't think about if you're just trying to come up with a solution by hand. Of course, every parking space would be reachable from the entrance. But our algorithms don't know anything we don't actually tell them. So we're going to have to think about how to model that. And the problem is just going to be to maximize the number of parking spaces that we can fit into this region. So how could we go about doing that? I forgot what my next slide was. In any case, this is the paper that was published a year ago in Transportation Science. Transportation Science is a very prestigious journal in this area. It's where all of the big work in traffic modeling and that from a deterministic or stochastic point of view goes, essentially from the operations research side of things. They come up with what are called network flow-based formulations. Don't worry about that because we're going to show you something different. Anyway, so we're going to have some sets. Here, S is just going to be the set of 1 by 1 squares in the lot. That's what I showed you earlier. And we're also going to have the set P of all of the possible legal parking spaces. And then the set D of all the possible legal 2 by 2 driving tiles. And we can just compute these sets really quickly at the start, because for each square S, there's at most 3 tiles that we need to check whether is going to be in one of these sets. F is just going to represent the driving tiles that have to be active. In our example, that's just that strip down the side. We're also going to denote the entrance tile by E. And then we're going to introduce some binary variables. So here, for each parking tile, we're going to have an X variable, which is going to be 1 if and only if that park is active. And for each driving tile, we're also going to have a Y variable, which is 1 if and only if that driving square is active. And we're also going to have the ZS variables, which are 1 if that square is a driving square. And this might seem a little bit redundant, but it'll become clear shortly why we have these extra variables. And it's also going to be useful to define some neighborhoods. So here, n subscript d of p is just going to denote the set of driving tiles adjacent to a park p. And that's just one of the 4 potential 2x2 driving squares that could be perpendicularly adjacent to any parking square. And we're also going to have the set of driving tiles adjacent to each driving tile. And so that includes up to the 4 overlapping driving squares and the 4 properly adjacent driving squares, because remember, these are 2x2 driving tiles. And then we get this example of an integer program. And if you haven't seen integer programs before, don't worry. I'll talk you through what this is step by step. So here, equation 1, this is just saying that we want to maximize the number of active driving tiles. Here, this sum is just the number of driving tiles which are active, because remember, it's active if the binary variable is equal to 1, and it's inactive if it's 0. Constraint 2 here says that a parking tile can't actually be active unless at least one of its neighboring driving tiles is also active. Because you can see in this sum here, if all of the y variables in this sum are 0, then all of these driving tiles in the neighborhood are 0, and we get the right-hand side equal to 0. That forces this binary variable to go down to 0. Constraint 3 just says that any driving square that's active forces the corresponding z variables of the underlying squares to mark that as a driving square. And then constraint 4 here says that every square is either a driving square or it's covered by one of the parking squares. And again, since these are binary variables, this also says that the parking tiles don't actually overlap. And equation 5 just says that the driving tiles that have to be fixed are fixed. And so what we can say is that a binary vector, x, y, z, which satisfies all of these inequalities and equalities, and which maximizes this linear function, is a solution to our problem. With one small problem, we haven't actually made sure that all of the parking spaces are reachable from the entrance yet. So remember how I said, the model doesn't know anything we don't tell it, and nothing about these constraints actually says that I need to be able to drive to all of the parks. And so it takes a very short amount of time to actually compute this optimal solution to the problem as I've given it in that previous slide, using some very powerful solving software like Arobi, which I'm not going to go into, just treat it like a black box. We can solve nice enough integer programs. But we need to think about how we can actually repair this solution. So I'm going to let x prime, y prime, and z prime represent a fixed solution to the master problem, that IP that I just showed you. And we can actually compute the set R of these disconnected regions of driving tiles. And in this example, you've got 5 of them, the entrance one, and then these 4. And observe that if there's only one region, then we are done, because that region contains the entrance, and all of our parking tiles are adjacent to a driving tile, which is in that region, and so we can get to the entrance. But if there's more than one region, we're going to add what are called feasibility cuts to the master problem, which are essentially going to exclude that solution from the feasible region. And so one thing that we could just do is add a feasibility cut, which just says, no, don't accept that solution, and then keep going. But that's just going to be an exhaustive search, and I shouldn't have to convince anyone here that that's a bad idea. So what can we do instead? Well, for each of the regions, we can consider the set of strict neighboring driving tiles for that region. That's just the set of the driving tiles that surround that region. So consider this particular 3x3 region in this example. That's just going to be the set of these driving tiles that are one out of it, that overlap it, and then the set of proper adjacent driving tiles to that region. And the union of these two sets, that gives us our neighborhood for that region. And then we observe that in order for this region to ever become connected to the entrance, at least one of those driving tiles must become active. you can think of it, we sort of want to push outwards from these disconnected regions towards the entrance. So what we do is we are able to add this feasibility cut, which is just a new inequality. This essentially says here that if none of the y variables corresponding to that region are active, then the right-hand side is 0, and that turns off all of the driving tiles in that region. And basically, what happens is we iterate between solving the master problem, checking the feasibility, and then adding feasibility cuts if necessary. And I've just glossed over a whole lot of technical detail that is interesting, but we don't have time to go over that. But in any case, eventually we can get to an optimal solution that has one region and satisfies all of the rules for our problem. And you can see that we've managed to fit 36 spaces in that parking lot now. But there's one problem. This actually still takes a long time to do. So there's a few things wrong with the formulation. Probably the most obvious one is that there's a very large number of legal packings of those tiles. There's a lot of different ways that you can check. And even if you limit it to the somehow obvious ones, you've still got a lot of things to check. But that's actually not the main problem with this. Modern integer programming solvers are very, very good, and we can spit up and chew out problems with hundreds of thousands of integer variables, depending on the strength of the formulation. And it gets a little bit technical, but the actual problem with this formulation is what's called the weakness of its linear relaxation. And if you want some more details on that, I recommend taking Math 3202. But basically, what I mean is that if we just forget that these are binary variables and we just allow them to be continuous variables, then you can get partially overlapping tiles in this. In fact, for each square, you could have all of the 4 overlapping driving tiles equal to 1/8, and all of the 4 overlapping parking tiles equal to 1/8, and this constraint is still satisfied. So this is a very weak linear relaxation, and integer programs are easier to solve when they have strong linear relaxations. So the question is, how can we actually improve on this formulation? Unfortunately, we can't without sacrificing optimality. But we can consider some very good heuristics where we're going to try to compute some good solutions very quickly, but we're going to sacrifice our optimality guarantee. And the basic heuristic is going to go like this. We're going to consider the directed graph with node set equal to just all of the parking tiles. We're going to have all of the possible edges between adjacent parking tiles. And we're just going to remove all of the neighbors of each tile unless that neighbor is closer to the entrance than D. Than that tile, sorry. And so why does this make the algorithm go faster? Well, it's because it's actually reducing the number of directions that we can expand those disconnected regions out from. And this drastically reduces the number of feasible solutions. But of course, since this isn't actually, this may accidentally cut off the optimal solution. So that's why this is a heuristic. We can't guarantee that this will actually give us the optimal solution. But as I noted on the previous slide, it actually does give us the optimal solution for the example that we've been looking at so far. Okay, but what about other examples? What if we added some extra obstacles to the parking lot? So here I've taken the same instance and I've just added a really annoying strip of obstacles in the middle of the parking lot. And then what you're seeing is actually the output of that heuristic. The first thing you'll notice is that, well, maybe it's not the first thing you'll notice, but it's the problem here. This driving lane, because it wants to move closer to the entrance in that network of neighboring driving tiles, it just goes flush around the obstacle. And it's not hard to convince yourself that that's probably not what we want to be doing if we want to maximize the number of parking tiles. And you'll notice that there is 32 parking tiles here, so we can't be sure that that's actually best, and we suspect that it's not. So let's try a different heuristic. We're going to do essentially the same thing. We're still going to remove this, the neighbors, unless they're closer to the entrance, but now we're going to consider 2 metrics. So we're going to remove them unless they're closer with respect to at least one of these 2 metrics, the same one that we just had. So if they're strictly closer, that's fine. but also this one where we penalize the distance of the edges according to the number of adjacent parking tiles. So this penalty function here essentially just says that the edges are longer when there aren't as many parks nearby. This is because we want to avoid those obstacles. And so now when we run this better heuristic, you can see here that we actually managed to skirt around that obstacle, giving it a fair bit of breadth, because the edges that live over here are going to be shorter than the ones that are closer to the obstacle, because there are more potential parks. So each of the driving squares over here, for instance, this one has up to 8 potential parks, whereas this one only has 6, and this one only has 5. And so now we get 34 parks, which doesn't seem like much, but remember, these are fairly small parking spaces, and I think these instances are mostly relevant to the kinds of car parks where it's going to be all day parking in relatively small spaces, right? Like Dreamworld doesn't care if they have 2 extra parking lots, but when you have a very limited number of space in a very congested urban area, you might care a lot about getting 1 or 2 extra all day parks. So we've done better. But again, I can't guarantee to you that this is the optimal solution because we are now just running a heuristic. There will be more computational tests coming soon if I feel like it. I was hoping to have more impressive results to share with you today, but I didn't get around to it because I have other things that I'm working on as well. I'm trying to get a hold of the actual instances from that other paper that we were doing, and the question will be is that does this heuristic produce better parking lots than the heuristic in that paper? Because I've already conceded that I can't solve the problem to optimality for some larger parking lots, neither can they, so it's going to be a game of whose heuristic is better if we decide to pursue this research any further. And I spoke a lot faster than I intended to, so that's the end of my talk.
Yeah.
Yep.
Is it like maybe I like this a bit, but does it work if like you have some like obstacle with a hollow region inside that like it doesn't try to put cars in there?
It wouldn't try to put cars in there. Well, it might try, but then all of those possible solutions will be eliminated by the feasibility cuts, and you could show that formally. So you could put a car there, but then you can only put a car if you have a driving tile next to it, and then it would say that tile cannot be active unless I can connect it to the entrance. That's sort of the in-words way of describing what this this cut is. This is this tile can't be active unless I can push it out towards the entrance. But that's possibly a class of potentially difficult instances because it might try all of the ways it can pack tiles in there only to forcibly discover that they're all infeasible. So yeah, that could be a problem. You were first, I think.
Are there any orientation constraints for the parks?
Yeah, all the parks are perpendicular parks. You could consider parallel parking or angled parking if you want. You just have to change the model accordingly. But I'm just considering perpendicular parks here. I reckon it would be complicated if you had both perpendicular and angled parking because then the whole like grid aspect of it starts to break down.
Yeah. That'd be like a non-integer program.
Maybe, probably. The reason we like integer programs, or rather linear programs, is because they're quote-unquote easy. Non-linear programming is hard. Not just in the formal sense, but in the practical sense, because it's all NP hard. All of this is NP hard, but Groby cares not for your NP hard problem. So.
Yeah, I was just going to say about if you had a hollow obstacle, maybe you have something to say about this, but you could just ban, like you could just say the obstacle is not hollow in terms of integer programming, just like this. You can't park in anywhere.
Yeah, I suspect that if you actually had because these are, we aren't talking about parking lots that are millions of kilometers large. You could probably just pre-process that hole out and just fill it with obstacles and not consider that.
Yeah.
But of course, that's manual work. But generally, in practice, some company is going to be like, hey, help me fit more parks. And then they'll go to a company and they'll just do it for their problem and then give them their parking lot. So we don't so much care about a little bit of manual pre-processing in practice.
Yeah, so okay.
Sorry, how do you guarantee, you mentioned the perpendicular path, how do we guarantee, how do we guarantee in our model setup that the paths were all perpendicular to the rows? Opposed to, like, the
Yeah, that's a good question. I did kind of gloss over that. Where I say here, P is the set of all legal 1x2 and 2x1 parking tiles, I only generate legal parking tiles. So basically, in the algorithm, I just go for S in S, and then I check. So if I've got a square, I check. So, you know, starting with the first one, I check, is this tile in it? Is that tile in it? If they are, I add them. Obviously here they're not. And then, so hence that's the, I've lost the slide. That's the 3S steps. So I check, for each square, I just check 3 tiles and add them if they're legal. So, yeah.
sorry, like, when you say if they're, are you doing this parking have, like, doesn't whether a parking tile is valid depend on the road that you generate?
I'm sorry, say.
Doesn't that depend on the road that you generate?
Oh, yeah, you're right. So P and D here depend on the instance. So given a particular instance, I generate P and D ahead of time. That's what, so the formal word for what this is called a priori column generation. And the reason it's called column generation is because we're actually adding columns to the constraint matrix in a linear algebra sense. But yeah. The point is that we can generate all of the possible parking and driving tiles ahead of time really quickly. And the other models don't do that. They just have variables for the individual squares, which are either parking or driving tiles, and then very complicated constraints, which give it the geometry. Whereas, for instance, this rule here, that driving lanes must be at least 2 squares wide, that's the most difficult part to implement in the other models. Whereas here we get it for free because we only generate big enough driving tiles. So I say we. Technically, the students who did the 4202 project are the ones who came up with the variables. Well, not the Z variables, we added them. But cool. Awesome.
So that's it for today. There'll be pizza outside soon. But as for next events coming up, in week 13, we have our wine and cheese on Friday, so please get a ticket. It's $10. You know, wine and cheese all night until we run out. On the Thursday of week 13, there's also a movie night between a bunch of societies, including UQCS and MSS. We're watching Goodwill Hunt. Yeah, I haven't seen it, so I'm pretty excited. We don't have any sponsor events. No more industry events this semester, hey? Yeah. So, yeah. Do you want to talk for UQCS?
So UQCS next week we have Juan's game hacking talk, should be pretty cool. He pretty much built a engine for validating using machine learning. Which is pretty damn cool, so I'm kind of excited about it. And then after that, yeah, we have that movie night, and then week 13. Actually, no, that is our week 13. Come on, the movie night. Apart from that, that's us for the semester apart. Semester drinks. That's all the something.